accelerometer. The first thing to notice is the x-axis. We're talking about tens of milliseconds. So you're charging over hundreds of milliseconds, and you're discharging over tens of milliseconds. The second thing to notice is that the drop in voltage is approximately linear. So what we would expect is you just put energy into a capacitor, and then you pull energy back out. But the WISP uses a linear voltage regulator. So when your linear voltage regulators run at very high voltage on the input end, it basically burns off all of that energy as heat. So you're just throwing all that energy away. So when you're thinking about how much an operation costs in the WISP, you can't really say it uses this much energy. Actually, what it does is it drops the capacitor voltage a certain amount. And that's pretty close to static no matter how full the capacitor is charged. Where the amount of energy is going to be different, whether you're at 1.8 volts or 2 volts, you'll actually use a different amount of energy. So for all of our work, we're now looking at the voltage drop of a particular operation.
The accelerometer doesn't look
Right. So an accelerometer, when you run it at higher voltage, it actually burns more energy. I mean, you look at the data sheet and it says if you run it at higher, it will use more energy. So this is just running the CPU, not the sensors. So now we look at how do you estimate task energy. So if you look at the right, on the table on the right, these are all those commands that build up Gen 2. I don't have the extra commands for read, but I do have the totals for the read command. So we look at the V drop, and we actually did this analytically based on the data that we plotted, and then we actually experimentally gathered data with that monitoring board. We saw that these numbers match exactly. So estimating energy is difficult because once you use Gen 2, you now have a non-deterministic MAC protocol. So you may have to you may have to respond to any number of messages. So it's very hard to determine what your energy cost of your task is going to be. So what we do is we actually, the way we answer what voltage is charged to is basically adaptive. So these tasks for us, we're trying to get sensor data repetitively. So we can actually just adapt the starting voltage until it works. So what we found is that sampling voltage, the amount of energy that consumed was mostly determined by having the processor active at all. So what we did is we actually we found that you don't actually need to let the voltage sample settle out very long, like Dan was talking about. You can actually do it very quickly. And you can actually do it fast enough where you can fit it right in the preamble of every reader command. So at every reader command, we get basically a voltage sample for free. So what we can do is when we're approaching 1.5 volts, we just go to sleep and charge back up. So we never lose our state information. So then our adaptation is basically, if you're getting close to 1.5 volts, go to sleep and increase your starting voltage. And if you end the task and you have plenty of extra energy, then you should decrease your starting voltage. Second one is how long to sleep to reach the target voltage. So what we do is we wake up periodically, but if you wake up too often, you burn energy. If you wake up too infrequently, you're going to overshoot your goal. So what we do is we exponentially adapt the polling interval. So if you sleep and then you wake up and you realize that your target is still twice as far as whatever gain you had, then you double your sleep interval. And conversely, if it's half as far away, then you decrease your interval by half. We found that this approach got us to within 0.1 volts of our target with a 16% overhead as far as charge time in the worst case. But 10% of this came from the fact that we have to have the processor in a different low power sleep mode to keep the oscillator awake. So if you're not using a hardware voltage supervisor, you're already going to have this 10% hit. So we weren't too far off from that best case. So to look at our adaptation, the box plots on the top are the starting voltages, and the set on the bottom is the ending voltage. So as you can see, as you move further away from the reader, the input power is less. So what we need to do is store more energy before we begin execution. So you can see that the starting voltages begin to climb. And then when they reduce at the end, that's because the maximum voltage that we can store is actually below 2.7. And then what we also see is that the ending voltages are clustered right around 1.6, which is where we end. Otherwise, we would have blacked out and charged back up again. So the end result, just for the read, is this. So instead of ending at 2 meters, we can now actually read out to 3.25 meters. Now what we saw is at 3.25 meters, the capacitor cannot charge high enough to support that task. So this is what I mean by at beyond 3.25 meters, the read command is not a feasible task. We can't possibly charge up high enough, so we can't execute it. But anywhere else, we can, and actually works, in all cases, better than the default scheduler. And we also saw that our scheduler performs slightly less well than Query, but only at very close input powers where your read rates are very high anyway. So in conclusion, the energy-aware scheduler executes any feasible task. We'd use it to double the range of the Gen 2 read command, which should let us batch sample to increase our sample rate. But really, if you have any task that's repetitive, this adaptation scheme will find a right way to schedule it. The second one is we have a lightweight timer-based wake-up, which lets you choose a different voltage. So if you do have a task, and it is deterministic, so you basically can get a pretty good estimate of how much energy you need to store, you can use our timer now, where previously the only technique to really wake up was the hardware threshold, which was fixed at 2 volts. So this at least opens it up to other application programmers that don't want the adaptation. You can still now sleep to arbitrary voltages. Questions?
All right, thank you. So we have time for a couple. We're over time, but we'll take two questions or so. Go ahead.
Okay, so you mentioned that you were using you measured the voltage drop of an operation as opposed to, I guess, just its straight energy usage. So I seem to recall that the voltage drop of of any given operation should pretty strongly depend on the actual voltage on the capacitor at any given time. Do your observations square with that?
The voltage drop is about linear. There's a little bit of a curve to it, but it's basically linear.
We should talk offline. Right. I have some measurements that you might want to see.
Okay, Matt?
So knowing what you know now about how much energy is required to implement different operations in the Gen 2 protocol, having optimized them, would you choose a different capacitor than the one that is in place on the circuit? Or would you think there's room for switching another capacitor in?
It really depends what you're trying to do. I mean, you could maybe make it just small enough so that because the smaller it is, the faster it will charge up to usable voltage, right? So having it charge up to 5 volts is maybe too much because we were actually charging to 2.8 volts to do the whole read command. But what if you want to do long crypto? It might make sense to charge up to 4.5 volts so that you can actually do a lot of execution before you then have to go to sleep and charge again. So, I mean, if you change the size of the capacitor, you're going to change the kind of things that the WISP can support. So.
Okay, Josh?
Just one more quick comment. Another idea that's kind of related to this that we've talked about is the idea of a programmable supervisor. So if you had if the application code had the ability to tell the supervisor, oh, wake me up when you hit 2.85 volts, that could be really useful as a way to.
If anybody has a good, cheap way to do that, that would be awesome. Because these fixed thresholds isn't really going to work for a flexible tag.